Okay, so hi there everyone. We're now in our next video in number theory. As you can see, I am now using a different kind of background. Now a black background with a chalk like um, chalk like brushes or stroke. I won't be using this while I am answering since my sketchboard is kind of in a bad shape right now and it's lagging. Anyways, this is a continuation video for our Chinese remainder theorem, wherein we're going to give now the uniqueness proof of the theorem. We are done with the existence proof that there exists some solution, um, and it is true that there is indeed a solution for a system of congruences. So let's state again the Chinese remainder theorem, shall we? So it states that the linear system of congruences x is congruent to a sub I mod m sub I, okay, where the moduli are pairwise relatively prime, sorry, which means that they are GCD. The GCD of m sub I and m sub j is equal to 1 for all I and j which is not equal. Okay, so that's when you say relatively prime, and for all I between 1 and k, also j is also there if this is the thing that you want. It has a unique solution. It says that the modulo is m sub 1 times m sub 2 up until m sub k. That is just the product of all the moduli of this set of system of linear congruences. So we have proven again that there exists such a solution. We just need to, it remains to us to prove that the solution is unique for each system. Before we can even start with our proof here, we will be needing some power of these two corollaries before we will even start. So these corollaries is actually from the lessons of our module before. That's the was that again about the the linear differential equations, GCDs and LCMs, usually with the GCD and LCMs. But we're going to start this right now, okay, and recall them. We will call this the first corollary as corollary 3.2. And what does this corollary 3.2 say? That if if the positive integers, or shall we say, if a sub 1, a sub 2, up until a sub n, in which they are all positive integers in the natural numbers, are pairwise relatively prime, are pairwise relatively prime, relatively prime, then we say that the LCM, the least common multiple of all these a sub 1, a sub 2, up until to this a sub n is equal to a sub 1 times a sub 2 times a sub n. So that's our first corollary. We'll be using that in this uniqueness proof. Second corollary that we need to think of, we will call this corollary 3.3. Corollary 3.3. This now states that let m sub 1, m sub 2, up until m sub k, sorry, be positive integers, so they are natural numbers in short, such that m sub I, the certain I divides A, okay, for I between 1 and k, for I between 1 and k. So therefore, if this is true, then we say that the LCM of m sub 1. I don't know if I can fit this. I hope so. M sub 1, M sub 2, M sub 1, M sub 2. I think I cannot. Let's use the other line. Then LCM. Then the LCM of M sub 1, M sub 2, up until M sub K also divides A. Okay, so let's state them again. Corollary 3.2, if this collection of numbers a sub 1, a sub 2 up until a sub n, which are all positive integers, are pairwise relatively prime, then the LCM of all of these is equal to their product of all of them. And corollary 3.3, let m sub 1, m sub 2 up until m sub k be all positive integers such that m sub I, some I here, which is an element of this m sub 1 to m sub k, one of them, one of the set here, one of the elements of the set here, divides A for some certain I between 1 and k, then the LCM from m sub 1, m sub 2 up until m sub k also divides A, or also a multiple of A. Okay, so with that, we are ready for the proof or the existence proof. So we will need first to show, I cannot fit it here. Let's put it on the other side here. Okay, here we are. So now to show that the solution is unique. Sorry, modulo M, modulo big M. Yeah. Recall that big M is equal to small m sub 1, small m sub 2, up until small m sub k. Let me check that if that's small m sub k in our theorem. Maybe I use another letter. Yeah, that's small m sub k. Okay, so with that, we must have this. So to show this, we will be first, sorry, we must be first we will let this x sub, x sub 0 and x sub 1 be two solutions of the system, of the system. What we want to do is we shall show that x sub 0 is congruent with x sub 1 mod big M. Because if that's the case, so therefore um, saying that both of them are unique. Okay, so since we say now that since there are solutions, so therefore x sub 0 is congruent to a sub j, mod m sub j, small m sub j. And we also say that x sub 1, okay, is also congruent to a sub j mod small m sub j for all for um for all j between 1 and k. Okay, so if this is true, so therefore canceling up the a sub j's, so what we can have is by some congruence property from some operations of congruence property. So maybe you can see that on theorem 3.2 or 3.4 from our previous videos. We can say that x sub 1 minus x sub 0 is congruent to 0 mod m sub j, um, mod small m sub j. That is, by definition of congruences, we then say that Uh, that is, we say that m sub j divides x sub 1 minus x sub 0 for every j that we have, for all j. Sorry, for all j. Now, by corollary, actually we can justify it using here, just here we can stop that m sub j is one in the collections of all the m sub 1 of m sub 2 m sub 3 up until m sub k. So we can actually say that this m sub j is actually just big M. But let's do this step by step, shall we? So by corollary 3.3, that's the purpose of the corollaries. Corollary 3.3 states that um, if we have m sub 1, m sub 2, which are positive integers, such that m sub I divides a for all I from 1 to k, then the LCM also divides a. So therefore, from here, we can see that this one, we can state it here, m sub 1 divides a for all m sub I divides a for all I between 1 and k. So we can also see here that m sub j divides this one for all j between 1 and k. So therefore, we can say that this is also true for here. So the LCM of m sub 1, m sub 2, but the m sub k also divides a here in this part. So we will say that um, LCM, let's put it here down below, that the LCM of m sub 1, m sub 2, up until m sub k divides x sub 1 minus x sub 0. Okay? We also then, this is the due time for us to insert the corollary 3.2, but by corollary 3.2, let's put it down below. By corollary 3.2, we can say that the LCM of m sub 1, m sub, I need more space. The LCM of m sub 1, m sub 2, up until m sub k is equal to big M. Why is that true? Let's look at 3.2 again. So our last statement for for the application of 3.3 is the LCM of all these collection of numbers is divides x sub 1 minus x sub 0. Now x sub 2, corollary 3.2 states that if you have a collection of this and they are pairwise relatively prime, in which we say that these are all pairwise relatively prime from the theorem itself, that the moduli are pairwise relatively prime, and we know that all the big small n's are the moduli themselves, so we can accept three. We can use the corollary 3.2. We say that LCM of all of these is equal just to the product of all of this, and the product. Remember when we define big M is equal to the product of all the m sub 1, m sub 2 up until m sub k. So therefore, we can say that the LCM of this is equal to the product of all m's, which is equal to big M. Okay, I hope you follow that through. You can rewind the video if you want some more explanations about that. But just think that by application of corollary 3.2, we have ended up with this statement that the LCM of m sub 1 to m sub k, the collection of all these elements here is equal to big M. Okay, so since it's equal to big M, okay, therefore we can say by going back to the definition, going back to the definition of these equations, uh, applying it here. So since LCM of m sub 1, m sub 2 up until m sub k is equal to M, therefore, substituting this LCM m sub 1, m sub 2 up until m sub k, since it's equal to M, so therefore we can say that M divides this x sub 1 minus x sub 0. This is taken from this statement over here. Okay, hopefully you won't get confused. So since that is true, so by the definition, going back to the definition of congruences, so we say that x sub 1 minus x sub 0 is congruent to 0 mod m. I cannot fit that. Let's put it here. Therefore, we can say that so sorry. So x sub 1 minus x sub 0 is congruent to 0 mod big M. That is to say that since we have 0 on the other end, so we can just by operations of congruences, we can somehow transpose this x sub 0 to the other side. That is, we're just going add an x sub 0 here and then add an x sub 0 here. So that's possible by theorem 3.2 or theorem 3.4. So therefore, what we have is x sub 1. Let's put it here. X sub 1 is congruent to x sub 0 mod big M. So that is to say that x sub 1 is congruent to x sub 0. So therefore, the we can say that the solutions are unique. Okay, since they are different solutions here. So therefore, these solutions are unique. Thus, therefore, hence, any two solutions. Oops, sorry. Any solutions solutions of the linear system of the linear system. Oops, or maybe I can do this in this moment. Yeah, of the linear system are congruent modulo m, modulo big M. So we can say therefore, so the solution is unique modulo big M. And that ends our proof in the Chinese remainder theorem. Okay, so at last we have just ended the proof that there exists a solution from our previous video, the uniqueness proof, or rather in the existence proof rather, and the solutions are also unique from this video here. Okay, so I hope you learned something from this, and that's the end of it. That's the Chinese remainder theorem. So up next in the next video, I'm going to give you examples of how we can use this theorem, okay, in a system of linear congruences. The next example will be we're going back to Sun Tzu's puzzle, okay, and now instead of it by iteration, we're going to solve that using the Chinese remainder theorem or the CRT. So I hope that you would like and subscribe and see you in the next video. Okay, thank you very much.